Okay, I think now's as good a time as any to get started. If we have late people, then hopefully they'll not be too lost. So welcome. Thank you everyone for coming. My name is Cesar Sewell. I'm a research computing associate for the Center for Advanced Research Computing here at USC. I'd like to talk about high performance computing with Python. This is a new workshop and excited to talk about it. Also, it's totally new, so excuse the construction, I guess. But also there's basically there's one example at the core of this that we'll be going through. And it's a pretty silly example. So my hope is that after this workshop, people who are interested, maybe you'll have some Python code that you've been working on or something like that. And so first off, the idea is to give you some inspiration for what to do with your Python code and how to make it run faster and all of that. But also maybe start a little collaboration and see if we can get more real examples into this presentation. So with that, let's get started. Oh, and while we're here, let me share the slides in the chat. Where's that chat button? Okay, yeah, so if you want to follow along or you want to refer back to this later, there's the slides. Okay, here we go. Next slide. There we go. It's working. Okay, so first off, we're going to do some quick setup. If you want to follow along, in theory, you can. I don't know if people actually follow along on these presentations, but you could. But this is also for later on when you get the slides. Hopefully, this setup will help you kind of follow along at home. Talk about what HPC is. We'll talk about, given a certain Python script, how do you go about looking for room for improvement? And then we'll talk about running in parallel on a single node. And we'll talk about running in parallel on multiple compute nodes. So if you want to, you can go to our GitHub page. You can run this GitHub git clone. These are kind of the Python requirements. I hope you don't mind if I just skip this slide. It takes a little while to install, but so you can just watch along. But when you're at home, yeah, make sure you get these packages installed. And actually, this H5, oops, where am I? This H5 is a little bit of an involved process. So here's how you do that. All right, so what is HPC? That's kind of like a why are we here type question. You get a little bit philosophical, but basically the idea is you have a problem you're trying to solve, and it's so big that it either takes a long time to complete, or it's so big that you actually can't fit it onto one computer, and it just will never complete because of that. So the idea is that you have lots of computers and they all work together, and you can share the load, or you can share memory across different computers, and they all work together, hopefully in harmony, and they make your problem solvable, or they solve your problem faster. So in general, I guess we'll talk about just like getting better performance. And so in general, here's some ideas first is make sure your code works. You could have very fast code, but it doesn't matter if it doesn't do anything useful. So yes, make sure that it works correctly. And once you're getting good results, only then do you start thinking about making it run faster. I guess you can, while you're thinking of it, you could be thinking of ways to run it faster, but I guess your main goal is just get it working. It's okay if it's slow. Then what you do is something called profiling. You run your code through a profiler and it tells you how long your code takes and what pieces take longer than other. And that is a useful tool for identifying where to target your efforts. So once you've decided that you want to improve your code or improve as in make it run faster, here's some tips, some very brief tips. Simplify when possible, meaning there's sometimes your code is doing extra work. And so of course, if you don't do extra work, you can go faster. Then there's something called vectorizing your code, which we'll talk about later on. Probably as a last resort, I would say parallelize, because it adds a lot of complexity. But yeah, there are problems that are well suited to parallelization. And we'll talk about what does it mean to parallelize. But I mean, in general, it just sounds like running multiple stuff at the same time. And another good recommendation is to use existing solutions, meaning don't reinvent the wheel. There's a lot of people out there, especially in Python, that are solving similar problems to what you're solving. And some of them are quite smart. And they've probably created some kind of solution to what you're doing, and it's very efficient and all that. So not just from a code performance standpoint is it better, but also like a human time. It's better if someone just has written the code for you to use it. It saves you time. All right, so I mentioned profiling a little bit earlier. Oh yeah, so this is a little bit what I said earlier. Probably you could tweak and fine tune code forever and it'll get a little bit faster, a little bit faster. So at a certain point, you get diminishing returns and it's just not worth the effort to make your code run faster. So it's okay if not the most efficient thing in the world. I know some people, they like to cement jobs overnight. So really, as long as the code runs within like 8 hours or so, then it's fine. We're talking about making code that runs a week or maybe a month and cutting that down to like a couple days or so. So basically, if it's impossible without profiling, or sorry, without optimization, yeah, then it's probably worth your time. Or maybe you could look at a bigger scale than what you've been doing before. But anyway, so profiling, like I said earlier, you run it through a profiler. It times your code, tells you which parts are slow and which parts are fast, or more like which parts take a lot of time and which parts don't take a lot of time. And from there, you can look at the whatever takes the most amount of time. That's probably your biggest opportunity for improved performance. So once you go and make some changes, then you can run benchmarks and compare different solutions. And that'll give you an idea of like what to do next. So the tools we'll be using for profiling are this built-in Python package called cprofile. And then later on, we'll use viz tracer because cprofile doesn't work for the multiprocessing example that we'll be doing later on. And these produce binary files, and there's another utility called snakeviz, which can read these files. So if you're going to run this on the cluster, you'll have to transfer files around. And that's what I'll be doing. And then for benchmarking, there's good old-fashioned time. You can basically get a start and end time. You put a stopwatch at a certain point in your code, and then you put you stop the stopwatch at a certain point, and you just get the raw how much time has elapsed. And so that's a pretty naive method. And actually, I have some of those in here. But if you want to get really fancy, there's something called timeit, which sometimes when your program is running, the operating system is running a couple things at once. So timeit gives you a better representation of how long your code specifically ran. And you can run it a bunch of times and it'll give you statistics. Next slide, here we go. Now we're getting to something more interesting. So I have this example. It's called write.py. And as you may expect, or may be thinking, yes, it writes files. So let me change my screen that I'm sharing. And we can take a little tour of write.py. Here I am, I'm in an interactive session. Already got it going. So I've already run git clone, and I cloned that repo. So there's the slides, it's index.html. Hold on, Zoom's kind of in my way. Can I move this? All right, perfect. So if I do ls on examples, so there's a directory of all the examples that we're going to run. There's also some job scripts. So let's take a look at write.py so we can get an idea of, examples write.py. Okay, so here's my write.py. Oops, what's happening? There we go, end of file. So what write.py does is first it runs this main function. Inside main, gets command line arguments. It creates two lists of vectors, so an X and Y, two-dimensional data set. And then it takes the number of files that we're going to write, and then this I, and it goes to write data. So let's go look at what write data does. Write data creates a two-dimensional matrix, and using a nested for loop, it populates each individual element of our two-dimensional matrix based on the number of files and which file we're writing, and then it uses this fun and exciting math formula. So we're creating, I have a physics background, so we would say we're creating a scalar field. So that's what it does. And I'll run this code real quick. Create files in this output directory. So I'm going to, okay, it's the correct Python. So I'm going to run it Python 3 examples write.py. And it tells me it's writing 15 files, and they're each going to be a 100 by 100 data set, and then just some diagnostic information. So if I do ls output, there's our text files, our 15 text files. Data. So it's kind of unreadable. So you'll have to take my word for it because I'm not going to count it out for you, but there's 100 going the horizontal direction and it goes off the screen. And then there's 100 lines. All right, so that's the code that we're going to be looking at. So can we improve the performance of this code? Yes, we can do that. And perhaps just by looking at the actual Python script, maybe there's some people screaming at me already at all the horrible things that I've done. But let's say we don't know, like, you know, as far as we can tell, it seems fine, it runs, whatever. So what we could do is we could go line by line and see, does this work? Could this run faster? But that's kind of tedious, and it doesn't really tell us where should we focus our efforts. So we're going to do the profile method. To run this code through the profiler, this -m c profile and -o, profile data, right. So I'm going to tell it, it's going to create a profile log. So I'm going to tell it where to save it. And then I'm going to tell it which script I want to write. I want it to run. And I'm going to give it this option of N100. So it'll be a little more substantial. So it ran. Let's check our output directory. There's 100 files. LS profile data. We have this new file, write.log, and we can look at it, profile data, write.log. And I'm getting a warning. It says this is a binary file. So yeah, it's not that helpful to look at. So what do we do? Well, like I said earlier, we're going to use snakeviz. So what I'm going to do is I've got an SFTP client running. So I'm going to take this write log. I'm going to copy it to my local computer. And let's see. OK, awesome. It worked. Oh, it didn't. OK, screen sharing pauses when you switch tabs. OK, that's not a problem. Oops, am I sharing my whole screen? OK, here we go. There's just my terminal. So here's my write.log file, which was generated by cprofile on the cluster. So what I'm going to do is I'm going to run snakeviz. Look at that. It's already populating for me because I've done this before. So snakeviz, it's already been installed on my local machine. I'm going to run it. And then it says web server has been started. Go to this place. And because of the way Zoom screen sharing works, you don't notice this, but on my web browser, new tab has popped up. I'm going to move this Zoom box out of the way again. It's just getting pushed around my screen. OK, so here is snakeviz. This is my program. It ran for about 4 seconds. And there's different ways to look at it, but this is a really helpful, especially if you've never profiled your code before and you aren't sure of the structure, but it kind of tells you, your whole program ran for 3.92 seconds. The script itself did some work, and then there's all this other, like, what appears to be Python startup stuff. And then we can see that there's different functions and all that kind of stuff. So I'm going to click on main, because this is what I actually wrote. This is the stuff that I have control over. And we can see main runs for 3.2 seconds. And main, mostly what it does is it calls this function called write data, which you saw earlier. Write data, in turn, calls a function called generate data, this thing called save txt, which is that numpy function we saw earlier. This is what actually writes the files. And then write data itself actually runs some stuff itself. So this is about half of our code is generating data. A quarter of it is saving text files. And then this is, it kind of lumps it all in. But presumably, the other quarter is write data itself does some stuff. So if we were looking at how can we improve the performance of this code, this generate data is the biggest one. So that's probably, it's also stuff that I'm kind of lumping you into what I did now. So we wrote this generate data function. So we probably have the most opportunity for performance improvement here because probably something that we did is not super efficient. This is a NumPy function. So NumPy is used by lots of people. So probably I don't think I can do anything smarter. I don't think I'm smarter than the NumPy folks. So I think I'm just going to have to live with the performance here, but we can look at this. Another thing I'd like to draw your attention to is there's a table here, which is a text representation, and you can sort. And right now it's sorted by the total time, but I could do something like sort by number of calls. So generate data is called, looks like 1,000,000 times. 1, 2, 3, 4, 5, 6. Looks like 1,000,000 times. So that's a lot. So per call is very small, but it's called 1,000,000 times. So this is also another place to look into. If you have a program that's or a function that's being called a ton of times, it's probably a good place to look. But I think total time is best. All right, now let me, where's my, here we go. And let me just change my screen one more time. Screen sharing has failed. Oh, failed to start. Okay. Oops. All right, so one more thing about C profile, which is if you don't want to go through the hassle of like creating a log file and copying it over to snakeviz and starting snakeviz, C profile has an option where you can just have it display a table directly to the terminal. So here it is. Personally, what I like to do, so it's a little bit hard to read. Personally, what I like to do is redirect the output. So I'm just going to call it log. So you can save it later and refer to it. So it saves everything, and it should, you should be feeling a little bit of deja vu because we have this end calls, there's generate data, save text, write data. So the top three that we were looking at earlier. Okay. Oh, screen sharing, so much fun. Okay, let's go back to the slides. Okay, so here's our snakeviz view. Oh yeah, there's also this other mode called sunburst, which looks really cool to look at, but I don't know if it's that helpful. It's kind of confusing to me. So we'll just ignore it, sunburst mode. But yeah, so we saw this, generate data, NPy.io, so writing text. So here's the code in our write.py. This is the write data. So there's a double for loop. Anytime you see a double for loop, probably that's where you're going to see some bad performance. So we see generate data itself. There's nothing we can really do too much about it, but we're calling it 1,000,000 times. So we probably are doing something wrong. So now let's talk about vectorizing code, because that's actually going to end up being the solution for this part. So vectorizing code, it's basically when you are running, you're applying an operation to a set of data, which is what we're doing. We're applying this generate data function to a bunch of two-dimensional matrix. So it's basically, it's a way that if you're going to apply an operation to a whole object, there are some optimizations to be made, knowing that it's going to be doing the same thing over and over again. And so this is a very common task that people like to do. And so people have thought long and hard to implement a solution to this. And in our case, the NumPy package uses some, I believe, C code. It can do this in a much faster version. So let's see, what's on the next slide? So what we're going to do instead is we're going to change the way that we're writing, that we're generating the data. So this looks a little bit simpler. We're going to call it generate data on this X, capital X and Y values. And these X and Y values are something called a mesh grid. I don't want to get like too much into the details of this, but the idea is, let's see, you're going to kind of have to do some research yourself into like, I guess, how can you improve it? So let's say you go and you do some research and you probably go on the internet and type in like how to apply a function over a lot of data. And eventually you might come across numpy.meshgrid, which is, I don't know if I want to read this, but it makes ND coordinate arrays for vectorized evaluations, blah, 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 scalar vector fields over ND grids. So that's exactly what we're doing. It's almost eerie how that's exactly what we wanted to do. Yeah, it's a very common operation. So if you're doing something that you think probably other people are doing, yeah, try and do a search, and eventually you'll find, hopefully you'll find something like this where someone has implemented the feature. I'd say the downside to this mesh grid option is it's kind of like the data structure has to be rethought a little bit. But when we look at the code, it kind of just makes sense. You apply generate data to X coordinates and Y coordinates, and you get like this two-dimensional array. So we have an example here. Examples right vectorize.py. Oh yeah, the other thing is that everyone's code is different. So it's hard to give a specific advice to every situation. But in this case, this is a very easy solution. You use this numpy.meshgrid option. Let's see, what do I want to do next? Let's just run it real quick. Actually, let's not run it because you know what running code looks like. So we'll show you the slide. So this is, if I were to run it, this is how it would look. Python 3-m C profile, total time. This appears to be a typo. So I'm just running this write vectorize.py example and redirecting it. And so the top few lines, I've just compiled them into a table. And so we have some similar, familiar looking stuff. We have this numpy IO save text, IO open, generate data is now way at the bottom. Oops, here we are. Oh. Go back. Okay, so on this slide, I'm just going to compare a few functions from the old code and the new code. So in this example, the old version ran, it took 4.8 seconds, and I think this is running on my laptop. And the new version on my laptop ran about 1.4 seconds. So you can see in the old version, it took about 3 seconds to generate data. And in the new version, it's like half of a tenth of a second or something like that. It's like ridiculously fast compared to the new, sorry, the old version. What else we have? Save text. It took about the same amount of time, which is to be expected. Generating the data is faster now, but once you have the data, you're still writing it out. So that is expected that it hasn't changed. What else? This is interesting. Write data itself, the function. Remember, there is a for loop in there, a double for loop. And that actually takes, it's not insignificant. Sorry, it's not a lot of time, like this 0.001 seconds. But it does. Sorry, I'm getting mixed around. On the old version, it took almost 1 second to run. And in the new version, because write data itself is not doing so much, it's much faster. So just taking these 3 changes into account, or this one change, and these 3 different functions, that actually accounts for the reduced time. So can we make this faster? Yes, we can make this faster. But we kind of have to do some introspection. So the file that we're saving is a text file. And if we are willing to give up human readability, we can actually see some performance improvements by writing our data out in binary. And so here's some information, but NumPy, this is a really common operation. So you can save in text, you can save in binary. Oh, I'm glitching. Let me turn that off. So you have to think about it. Is it worth it to you to have human readable files? Are you going to really be looking at every single file? If yes, then probably save in text. If not, if you're fine with, if you're going to be doing something with this example data later, it might be okay to write in binary and maybe occasionally convert one to a human readable format. And the majority will be in binary. So with just changing the save function, I don't think I want to demo this. I think you get the idea. You run, make a little change in code, you can rerun it, and that's what I've done. And I got some performance results here. So I ran it through C profile. So the old version, we saw save text took 0.87 seconds. And in the new version, it's not save text anymore. It's just save. It took 0.002 seconds. So that's ridiculously faster than this save.txt. So you really want to think about, is it worth, do I really need human readable? I don't know, that might weigh heavily on your mind. But now we have this kind of, this new thing, built-in method io.open. That's the thing that takes the most amount of time. Generate data takes the exact same amount of time, which makes sense. Write data takes the same amount of time. So what is this built-in io.open? This is basically the opening having the file system open a file and have it ready. So now we want to think about, do we really need this to be faster? Do we really want to if we want this to run faster, we're kind of hitting infrastructure limitations, meaning probably our code is running as fast as it's going to run. And now it's is the file system going to be able to support our high performance? So if we want this to run faster, we're going to have to do some, I guess, other philosophical considerations of do we really need to be writing files? Do we need to write all of them? Do we need to write individual files? So that kind of stuff. So for now, we'll just ignore that, those philosophical considerations. And we'll just say, OK, I think this is probably as fast as it's going to go. Oh, yes, so pretty good. If we want this to run faster, I guess coding wise, I guess Python wise, this is probably as fast as it's going to be, unless we want to start opening up that io.open function and implementing our own stuff. So what if we wanted to do this faster, though? Is there another way that we could do this? And the answer, of course, is yes. We can run in parallel. So as soon as we're happy with the performance of a single threaded application, I think that's a good time to start thinking about parallelism. And parallelism can mean different things to different people. So here's a little bit of a survey of what it can mean, or different kinds of parallel. So there's this concept of data and task parallelism. What we're doing is data parallel, meaning you're running the same task, but with different data. And task is you're running different tasks, maybe with the same data. There's also this concept of pleasantly or embarrassingly parallel, meaning you run the same program and the parts don't really talk to each other, but you run a whole bunch of copies of the same program. And you may hear this referred to as high throughput computing. There's also this concept of implicit and explicit programming. So it could be the case that maybe there's a built-in Python function where we could write data. You give it a list of files to write, and it'll automatically parallelize that for you. And so that would be really great if such a thing existed, because we don't really have to take the time to create an explicitly parallel solution where you implement some parallel solution to your problem. Sorry, I got to take a quick water break. But overall, the idea is you want to get your program running faster somehow. And in general, if you can run on one computer, that's easier and also faster than if you can run on multiple computers. And we'll talk about why in a little bit. Oh, I guess we're talking about it now. So there are costs, or maybe even some would say penalties, to running things in parallel. So this is something that should weigh on you when you're considering parallelizing your code. It's not free, meaning it takes time. It takes time to parallelize your code. And what we've got running so far, even though it's a very simple example, it seems OK. We've got some good performance improvements. It was 3 seconds, and now it's about half a second. So that's a really good speed up. So maybe we're just happy with how it is. But let's say for some reason we want to run this program and write 1 million files. Suddenly that's going to be a little bit more, we'll say, scary. So yeah, maybe we do want to parallelize that. So now let's assume that we've we've decided we want to parallelize our code. Some considerations to think about are there's actually overhead. If we parallelize, we have to start processes. We have to copy data around. Maybe the processes have to communicate with one another. So those are things that we probably wouldn't have to deal with if we kept everything as a single core. Another thing to think about is we can run things in parallel, but we're not going to get, like, if we can run it on 2 cores, it's not going to run twice as fast, which seems counterintuitive. But if you think about it, only parts of our code can run in parallel. So like, let's say half of our code can run in parallel and we can make it take 0 time somehow. We still have the other half that is not parallelizable. So the best that we could do is 50% speed up. But that's in an ideal situation. So we would also have to consider like the cost of spawning child processes and communication and all that kind of stuff. So what I'm getting at is that there is a scalability that we'll run into and like a diminishing returns. And we'll look at that in a minute. So I don't know if the slide makes any sense to anyone, but we'll see some examples of what I'm talking about. And then since we're on an HPC cluster, you have to have hardware that can support parallelization. So usually that means at least having access to more than one CPU and having a certain amount of memory. And so on our cluster, you can read more about it on our documentation. But you can do something like sinfo2, and you can see what hardware configuration is available. And to request more than one CPU, typically you'll be doing the CPUs per task option. And we'll see that later on too. Oh, and then another thing, so I talked about explicit and implicit parallelization. If you have an implicit parallel solution, you can do both at the same time. So you can use other people's parallel solutions and you can use your own, but there may be conflicts. So you might be not have enough resources to support all of this parallelism and different kinds of parallelism. So one solution is to turn off implicit parallelism, and one way you can do that, of course it depends, but maybe you want to set this num threads, OMP num threads. So just keep that in mind. There is no example in this workshop where we have to worry about that, but just keep that in mind. Okay, so probably one of the first, if you haven't done any research into this at all, one of the first things that may come up when you type in running stuff in parallel on Python is this multiprocessing package. It's a built-in package. And the basic idea is you create a pool of processes and then you send work to those processes. And here's an example from the documentation. You have this function f, and it just takes one number and then squares it. And so in this example right here, it creates a pool of 5 processes. And then it does this map thing, and it maps these inputs to this function. So what it does is another way of saying what I just said is it takes 3 separate arguments and it runs f of 1, f2, f3 all at the same time. And so you're achieving parallelization through that way. So that's a very, very basic example. This is you apply a function onto different, I guess, input data. Input data. Since our So we're going to do this with write data, but write data actually takes more than one argument. So we're going to do this pool.apply method. And because of that, I also added this W option for a number of workers. So when we run this write multiprocessing program, we can, this is a knob that we can turn basically, and we can set the number of workers that we want to use. Okay, so let me switch my screen around. Let's go back to the terminal. Okay, so here we are. We're looking at some old profile data. Let me think, what do I want to do? If this is worth, so we can try this SSH. All right, so I've got in this bottom half of the screen, I have top running. And this is just a demonstration of like, what do I have running on this computer? Right now, it's just me running top in bash. So not a lot of activity. So let's see if I can get this demonstration to be helpful. So I'm going to do Python 3 examples, right? Multiprocessing.py. I'm going to give it, let's say, 1,000 files. And I'm going to have it run on one worker. So hopefully, if this works, I'll enter. And then on top, we can see there's 2 Python processes, and then they go away. And then if I do 2 workers, we should see an extra one. 1, 2, 3. So we can kind of see, yeah, look at that. It's actually running in parallel. OK. So let's run this through a profiler. And I guess I can demonstrate this since why not? Time. So I guess just demonstrate it doesn't work. Okay. That was a typo. Now let's run it. So we run C profile and we get this horrible. Let me close this top like that. Yeah, kill that pain. Okay, so we have this horrible death. It's just like getting mad at us. So it doesn't look like C profile likes multiprocessing, but that's okay because we can use this other utility called VizTracer. That's how it works. All right, this is how you use it. VizTracer. This is a Python package that's been installed previously. Log multiprocess. Then you give it the script that you want to run. So right, multiprocessing.py. We'll give it 3 workers. And let's just say 100 files. What happened? Could not convert string to float. Uh-oh, that's not good. Can't pickle. I swear this worked before. Okay, let's see. I think I have a copy of this result. So let's pretend that we didn't see any error messages. And while we're imagining that we're not seeing those messages, let me go onto my local machine, and I should have some result files. Okay. Let's see, is this? Okay. I gotta go back to my switching. Okay, so let's pretend we didn't see that horrible error message. And instead we see this Viz tracer has created results3.html, and then I copied it over to my local computer. So when it was working, this is what happened. Okay, so this is a kind of a confusing looking screen that we're seeing. So I ran this on 3 processes. So we can see there's 3 of these crazy graphs. This is what they refer to as a flame graph. So let me zoom in here. This is a really interesting, at least to me, it's interesting how this works. So it kind of tells you in like what sequence and what functions your code ran. So we can see like it does write data, then it does this get, then write data, and then this should look a little bit deja vu-y to when we ran in SnakeViz, right? There's a write data, there's a generate data, there's save, there's this io.open, and then there's another sequence of get, and there's an enter, receive bytes, get data. All right, so that's kind of what you're looking at. And we can see that there's different copies of this. So this may be a little bit inscrutable. So what's happening is so here's an iteration of our loop. So it does that apply. It applies those variables that we showed earlier to the write data function. And this iteration loop takes about 10 milliseconds. And 7 of those 10 milliseconds is this weird get, enter, receive bytes. And then two of those 10 milliseconds is actually writing data. So what is this? What's going on here? It's like most of, I'll just cut to the chase, I guess, which is most of this program is doing communication. It's sending data to a worker, and then it's spending way more time sending data to a worker than it is actually doing any work. So that seems bad. Oh, wait, I'm already sharing the correct screen. Let's see, can I do this? Is it going to get mad at me? OK, so here's Viz tracer. Here's a screenshot. It might even be the same file. This is when I ran, and then we're looking at Viz tracer. So Viz tracer is cool to visualize what's happening, but it's not so cool in terms of like creating that profiling table that we saw earlier. So here's, I've gone and manually created this table. And so for comparison, for one worker, when I ran this, our vectorized binary, right? Vectorized binary, that took about 0.3 seconds. Here's some, oh wait, sorry. Forget what I just said. So if we were to run this on one worker with these parameters, for one worker, it takes about 0.3 seconds. These are the top most time-consuming functions. So there's save, which is like the save data function. There's this thing called receive bytes. And then generate data, which we all know and love. For 3 workers, this is interesting. It took the same amount of time. And we have receive bytes still. We have generate data and we have save. So generate data and save didn't really change. in terms of time consumption, but we have this enter and receive bytes, and that's taking so much time. What's going on here? This is a communication overhead that we're seeing. So even though we have more workers and they're sharing the load, those workers, I guess, don't talk to each other very well, and they're not more efficient. They're not faster than one worker by itself. So yeah, we can parallelize, but it's not. It's kind of not worth it. What's going on? Why? Why is this? So what's going on here? When we run this pool.apply function, every iteration we're passing in x, y, output, n files, and I. So that's 1, 2, 3, 4, 5 variables. Of these 5 variables, 4 of them are constant, and 1 of them changes. So what's happening is this process known as pickling. I guess that's what Python likes to call it, or in general terms, it's called serialization or something. Serialism, I don't know. The word is on the slide is serialized. But the idea is you have an object, like let's say this cute jar of pickles, and this jar has little pickles inside. So if we wanted to serialize this jar of pickles, there's some function that takes this object and turns it into a one-dimensional stream of data, usually like a binary format. So it converts it from a jar of pickles into this sequence of numbers. And then, so that's when we do this apply. Then the worker takes this serialized data and deserializes it, turns it back into a jar of pickles. And so we're doing that 5 times for each variable. And some of this data is pretty complicated, like output, n files, I. These are all like strings in an integer. But x and y, these are NumPy mesh grid objects. So that's a pretty complicated process. And it's doing that 5 times. So for every iteration, it does that 5 times, and there's 100 iterations. So that's this serialize, deserialize process. It happens a lot. That's a lot of time. And only I changes. So that's really annoying that we're doing all this extra work. So just on that idea, there is some optimizations to be made. So we might have to think about how would we do that, but there is room for improvement. The serialization process is kind of annoying, but we don't need to serialize everything. So let's see, what's our next slide? Okay. So this diagram is kind of crazy looking. It kind of looks like an undergraduate social event happening. So the solution is we're going to use this multiprocessing queues ability. And basically the idea is each worker, we're going to give it some data when it initializes, such as X, Y, N files and output, because those don't ever change. Then we're going to use this queue structure to put in I, which is like the iteration number. So that brings us to the diagram. So on the left, we have process 0. And if you imagine a stack of cups, like those red cups that you have at parties or whatever, no one wants to do dishes. We're adding to the top of the stack of cups, and we're pulling from the bottom of the cups. So this is our work queue. So what's happening is our process 0 is adding data to the top of the stack, and our worker processes are pulling data from the bottom of the stack. So we still have to do that serialization and deserialization, but this allows us to not serialize as much. Then if we wanted to, we could have each process save data to like a results queue. Similarly, they put data onto the top, and process 0 pulls data from the bottom of the cup. And so we can have these processes communicate using this, this queue structure. So that's what I've done here. And I don't know if this is actually readable. I guess there's room for improvement on these slides themselves. What have I done here? Oh, OK. So what I've done is I've created my own custom process class. And this is kind of horrible to look at. I don't know if I would recommend doing this, given what we're going to do next. But you could, in theory, you could write your own custom process class. And as part of the creation of your custom process class, you can have it pass in task queue, a result queue, and then our size, output, end files, which we want it to do. And then once you do that, you have to create a special run method or function such that when you start this process, what does it do? So in this case, it pulls data from the queue, and then it does this write data. And then just for demonstration purposes, I have it say timing itself. So we could look at how long it takes to write a file. But that's just to get just to give you the idea of you can pass data out of the process back to the main. Sorry, you can have the worker communicate data back to the main process. OK. Let me think. I don't know if I want to run this code because we know what running code on the command line looks like. It's not very exciting. So I'll give you two nice, cute pictures. Let's see, these slides. Let me berate my slides for a minute. OK, so let's. So what are we looking at? We're looking at two graphs. So this method actually works. I was very surprised when I ran this. Yes, it works. You do have improved performance. But the scaling is not very good. And so that's what these graphs are showing. They're demonstrating the scaling. So on the left, I made those changes. And for writing a 100 by 100 data set, 100 files, or I think it was 1,000 files. I don't remember. So on the left, we have this little trail of dots. So we can see, based on the trail of dots, as we increase the number of workers, we get speed up. And we kind of see that it starts to like, I'm not sure of the mathematical aptitude or comfort of this audience, but this kind of looks like an exponential like decrease or something. It's not, it's kind of plateauing, or it's an asymptote. And then this crazy dashed line, this is if we had linear scaling, meaning two processes would give you twice the speed up, and three processes would be 3 times the speed up. We're not even seeing twice the speed up at 16 workers. It's going really slow. So it works, but it's not great. But if we increase the write size of 1 to 1,000, which means that the time for the communication to happen is low compared to the amount of work that's being done, we do get better scaling. You know, from here, we do get our double scaling. But yeah, so communication overhead is a big challenge. So for certain sizes of problems, it's probably better to just stay a single core process. In this case, I'd say for if you're writing a bunch of small files, probably do single core process. This, let me go back. This crazy diagram, which I'll use to represent my program, multiprocessing queue. This was really complicated to get working. I would say it was not worth the effort. It took a lot of time. I'm not even sure if it's actually optimized, but even so, like the scale up is not good. So maybe it's my fault for not having a good scale up. But I'd say just the amount of effort, the complexity of the code. If I were to share this with someone else, I'd probably need like a good chunk of time to explain like what's happening to people. And so if you're working with other people, like this is it's like time that you could be doing other stuff other than like explaining and documenting how your code works. So I'd say it's fun. It was fun learning this multiprocessing queue. But for this case, it's not really a good solution. Speed up is not that good. You do get speed up, but the time I put into it and just the complexity, confusion is not, it really weighs heavily on my mind whether or not I would do this again or recommend this. So what is another alternative? Oh, before we get into that, so if you were to run this as a job script, here's an example. So you would make sure to request CPUs per task, and maybe I'll add another. I'll update the script later to include the number of workers. But yeah, you would have to request CPUs per task, and what that does is that what this combination nodes one and tasks one CPUs per task, this guarantees that your 8 CPUs that you're requesting, they stay on one compute node. Because kind of a limitation and also kind of a good thing, as we'll see later on, is that everything stays on one computer. And if you have a CPU on some other computer, it's not going to be able to talk to that unless you do something else, which we'll talk about soon. But yeah, the Slurm job scheduler, you need to kind of coax it into giving it to you all on one computer. So what if we wanted to scale this program another way? You may have heard of something called MPI, message passing interface. And this is a method that allows people to have programs that communicate across many computers. And I think personally, this works better. And so we'll do this example. But the main benefit is you can scale really large. So before, when I showed you that we passed in that -w option for workers, the limit is the number of CPUs on a computer. So even if we were happy with the scaling and how well it worked, you're constrained to probably on our cluster to probably like 20 CPUs. I'd have to double check, but that's a rough ballpark estimate. If your program is so huge that it needs like 100 CPUs or 200 or something like that, you're going to have to expand beyond one computer. And you're going to have to start thinking about something like MPI. So luckily, we have MPI installed on our cluster. And someone has created an MPI package, which allows you to run MPI functions in your Python script. And so let's look at it. And personally, I think this is a better option. So here's another cute photo of what's happening. So we have another example, write MPI. And let's look at the picture first. So we have a data. What's going to happen is we're going to create some data. We're going to split up the data into some chunks. Then each process or each worker is going to be sent some data. And process 0 also gets some data. And then everyone's going to work on that little piece of data. And they're going to run the write data function. So in terms of code, what's happening, So like there's all this chunk and NP array split data size. There's all that kind of Python goodness. But what I want to call it to your attention is the MPI for Pi functions. There's com.send, so you're sending data. So there's a concept of ranks. So ranks is like the workers. So the rank 0 or process 0, it's going to be the one in charge of splitting up data and sending data. And everyone else is going to get ready for incoming data, and then they'll receive the data. And oops, the slide's a little bit out of date. And then once everyone has a little piece of data, then they're going to call write data. So we're splitting up the data, and then we're basically back to our write vectorized binary code, which we were so happy with the performance of. So there's only one communication spot, but this is just to give you an idea of how you would go about communicating. So let me go back to, let's see. Where's my terminal? Do I have it? I don't think I want to run code. I mean, you know what running code on terminal looks like already. So, so here's a benchmark of this MPI for Pi example. So there's some good things and some bad things about MPI for Pi in general, and this implementation of speeding up the code. So first thing is this com send and com receive. It's a pretty simple concept. One person sends data, one person receives data. So like from that, it's a pretty easy concept to grasp of like, oh, okay, you can create a workload manager. You can say this processor is in charge of sending data to everyone. And so you can kind of create your own manager. Another thing that I like about MPI for Pi is that we can use our old friend cProfile. And if you are interested, you can run your program through the debugger, Python debugger. It looks easier. So compare this with that other diagram. I mean, I don't know if it's very readable on this slide, but you kind of have an idea of what's happening. You know, rank 0 is doing this. Every other rank is doing this. You don't have to worry about like extending a process class, which I'm not sure how comfortable people are doing with that kind of stuff. So this is kind of gets to more of like why people like Python is you can just like have pretty simple code and stuff like that. Another good thing is it's very easy to scale up. You can just in Slurm, you can request 100 CPUs and tell your script, you know, go have fun with these CPUs, and MPI will deal with the communication, and it's okay if they're not all on the same computer. So what are some bad things about this? Kind of negative, right? There's always something wrong with every script that we have. Bad things is that the workload manager is very, very basic, at least in this script right here. It's basically everyone take a piece and do your own thing. If we wanted to, we could have our workers send data back to the process 0, and we can do all that. But yeah, we would have to implement that ourselves. So that's a little bit tedious. Another annoying thing is if we want to run cProfile, this generates a profile file for each process. So each process does its own thing, and so it creates its own log. And so you have to like, it's a little bit of a hassle, especially if you have more than a couple workers. So that's kind of annoying. So that's just another guess we'll say infrastructure thing that you have to think about as you scale up. New problems arise as you scale up. And so there isn't really a good method, good way to avoid this, but yeah, it happens. Another thing, which I think is the biggest one, is that this is actually not that much faster. Let me see, can I go back a couple slides? I don't know if there's a good way to compare these other than putting them on the same plot. So you'll have to take my word for it. It's not that much faster. In fact, it's slower than that crazy multiprocessing queue method. And why is that? Well, at least on this example, this ran across 2 compute nodes. So the communication across different computers, that actually takes time, and it's faster if everything can stay on one compute node. It's faster to send data to a local processor than it is to another processor on another computer. So that kind of makes sense intuitively. So because the communication is so slow, that's a really big penalty. So that's something to think about, but that's also you can't really help that communication. Is always going to be slow. And in an ideal world, your program is just always doing calculations and chugging away. But sometimes you have bottlenecks such as communication and file operations. But yeah, compared to the work queue method, even though it's slower, I still recommend this over that. Because the complexity is better and the performance is similar. So this goes back to the fast enough concept. But can we make this faster? And yes, because you can see I still have a few more slides to go. Yes, we can make this faster. So how would we do that? I'm guessing I guess I don't have a slide on profiling just because it was so tedious. But communication, it's very clear that the problem is communication. Not just in our, I guess, personal relationships, but communication between workers. So that's really the only thing that's added. It's like the only surface. So what can we do about that? Well, MPI for Pi has some convenience functions because send and receive is not, you could do almost anything with send and receive. But if you want to do something like send data to every worker in your pool of workers, the fine folks at MPI for Pi have given us this com.scatter, which is also just a normal MPI function. So the idea is that you have a data set or a list of data, and it spreads it evenly among all the workers. So this goes back to our using existing solutions concept, which is we'll just let the MPI for Pi people, I guess, do it for us. So here's our code. It looks simpler, but let me just kind of walk you through it. So we have data is generated. It's a list of data from 0 to the number of files. Then we do this data.reshape, and it goes off the edge of the screen. Sorry about that. Oops. So we have a list of data and n chunks, number of rows and columns and all that kind of stuff. And then we create this receive buff. So only the main worker does this data creation. Everyone else does this everyone does com.scatter. What that means is basically wait for data to come from the rank, and everyone gets a little piece of data. And then from there, we get back to our just good old-fashioned write data function. And so because we're using someone else's hopefully optimized and improved code, hopefully because of that, letting them worry about the details, we're getting improved performance. And actually, I can go back and forth between these slides. And you can see line goes up, line goes down. What that means is as these little dots, and they're red for some reason, oops. These dots are closer to the linear scaling, meaning that you're getting better scaling and they run faster. So yeah, it is indeed the communication. And do I have a pro-con list here? No. Oh, I forgot to add one thing. I guess I'll add this remark, which is you can kind of see there's gaps here. And so it turns out the way that I've implemented this, there must be one worker for every data chunk. And so it just turns out the way that multiplication and division works is sometimes you get uneven data. And so that's not the way this particular script works is not good. So I guess room for improvement is maybe we can look at this data sharing method. But yeah, overall, this works good. You know, maybe you just are confined to using certain numbers of workers and not others. I guess that's fine. Okay, we're getting near the end. The end is near. So another thing to think about is parallel I/O, meaning earlier we saw that almost 40% of our time was waiting to open a file. And you know, we're writing 1,000 files to the file system. And the files themselves aren't actually very big. So in general, this is like I don't want to say bad practice, but it's not great. It's better if you can do it, if you can manage the logistics, it's better to write one large file than lots of little files. And there's a lot of reasons why, but it's the operating system can do some optimizations for you. So this is just outside of the Python script, outside of any script really. So this concept, so there's parallel I/O. I bring this up for two different reasons. One is that if we wanted to, we could merge all of these files into one big file, but you might run into issues of like processes like, I don't know, have you ever been on a Google Doc with multiple people and everyone's editing it and it's pretty wild. You go to click on a line and that line shifts down. So something similar happens here. You have multiple processes writing to the same file. So there's different libraries like HDF5 or the Python implementation of HDF5, which is called H5Py, where they coordinate, every worker coordinates with every other worker when it wants to save to the same file. So even if you're not parallelizing, it's still a good idea to have one large file instead of lots of little files. So if we wanted to improve this code even more, one method is to use this HDF5 file. And I have this example. So starting with this write vectorized binary, which is like our golden child, using that as a starting point, we can create write hdf5.py. And so maybe you remember our write data function. And instead of using save numpy.save, we're going to use this hf create data set. And then hf is a predefined file, HDF5 file. So the change to the code is very minimal. So not only, okay, so but there's something to consider, which is before, you know, we had 100 or 15, whatever number output files, and they're written in binary, so it's not human readable. Now the data sets themselves are not human readable. You just have like this one blob of data, and you don't even know how many data files are in it. So I guess the downside is you need HDF5. If you do something like this, you're kind of committing to HDF5, and you have to use these utilities to process and pull out the data. But if you don't mind giving into a little bit of complexity, here's an example. What did I do here? Comparing write vectorized binary with write HDF5Py. I did 1,000 files just to really make my point here. I think the size was just 100 by 100. So here's the old version. io.open, basically out of almost 6 seconds, 1 second is just waiting for a file to open a new file and then generating data, which makes sense. That should take a long time. And there's this toFile method and this POSIX.stat. So this is all just associated with like waiting for a file to open and then actually writing the file. And then what do we have when we do our hdf5.py? Generate data takes the same amount of time as it always does. So 0.86, 0.87, same. Then we have POSIX.stat, which it runs more frequently, but overall it's less time. So POSIX.stat is like the operating system wants to look at a file. It's getting ready to do something with the file. And then make new dset, that's the HDF5 function of converting our data into a data set and writing it. So overall, we're getting a pretty good performance increase. We've changed a couple of lines of our code, but I'd say the complexity has increased a little bit because we're using a new data format, which is kind of scary and unfamiliar. And if you want to read data out of it, you need to have HDF5 in your code again, and you need to have like a read the file. And I think on my next slide, do I have it? Yeah. Reading data is a bit harder. I guess, we could have a whole presentation on H5Py, but you have to use this key object, key syntax to pull data out of it. So if you want a particular data set, you use a key to call it. Oh, and then another thing, so if we wanted to do our MPI version, you can see it in this right final example. It's almost exactly unchanged. We just add this driver MPIO and you tell it this COM syntax. So basically the syntax hasn't changed. You're just telling it MPI mode is on and you're giving it like some information about the current MPI world. So all the work, so it knows like what workers to listen to basically. So running an MPI job, here's an example script. We'll just look at the bottom first. So you use srun to launch your Python script, and you use this MPI PMI option. This is like a communication method. And this is the one that we find works best. And then this is what you might be used to. Then you run your Python script. The rest of it will work backwards. This is all the modules that you need to run your MPI. So if you wanted to, you could use OpenMPI, but there's other MPI implementations. You need this pmix, so we can use pmix. And then for requesting resources to run on, use n tasks instead of CPUs per task. And doing it this way, the job scheduler will find you 16 CPUs. Doesn't matter if they're on the same computer or not, and that makes it easier to find resources. If we wanted to combine parallelism, we could say each task does its own. If we want it to be like, I guess, masochistic, we could combine this MPI with our work queue option, and we could say each MPI rank can have its own little sub-process, and that also helps us minimize communication. But let's not, but the option is available to us. Yeah, so here's an example JavaScript. Okay, so that's all that I have. Oh, and there's a typo on my slide. So yeah, if you want to read more about any of these topics, here's some links, and I'll fix that typo. Here's some links to all the tools that we use. You can read the documentation. Documentation is always exciting. So thank you for attending. Thank you for your attention. If you have any questions, you can send mail to support@USC. If you want to attend more workshops, here's our workshop schedule. If you have any questions for me now, now is a good time to ask them. You can go ahead and unmute or just put in the chat. And I mentioned this earlier, if you have a Python script, I'm kind of looking to improve this presentation and have some better examples. It's fun to write 1,000 files, but I don't know if that's a really realistic example. So if you're interested, send me an email. Maybe we could get something working. But other than that, it looks like there's no questions. Oh, you're welcome. OK, well then, thanks for coming. Have a great weekend, everyone. Bye.